All right. So the first thing is I'm just gonna check this stream layout, make sure it looks good, and then we'll get going. So right down here, you can see what we're currently working on. Here you can see what we're next working on, and then here will be the source code. So I'll try to keep this area down on the bottom right for an overview of like where we currently are. So if you scroll through the video, you can kind of figure out what section it is. Then over here on the top right, I have Shader Toy. I've cropped it so you can see the entire shader. And then if we scroll down, we can see the shader source code. However, I won't be using this source code here. I'll be using the window over here for that. And then when I'm ready to update, I will copy paste this to the tiny URL here so that you can use it. And then I will also paste it over into this window, right? So the shader toy window, I'm just not going to use much. I find it's it's just not an editor I'm super comfortable with. So also when you make a mistake, oh boy, it just makes things kind of more confusing, I think. Or it's just very cluttered when something goes wrong because it doesn't show you the first problem, it shows you the cascade of problems, which I find very distracting. Okay, so with that, I just need to check twitch.com and get an idea of what this stream looks like. Does my layout actually kind of like does my layout check out? So I'm gonna just go to twitch.com. I'm gonna look at my stream really quick, and if my stream looks all right, like if I like the layout, then we'll get going. So let's see. Let's click my profile. I have no clue how to do this. Let's just do. Okay, so right now I'm in my top monitor, which you can't see, and I just want to, it's using a horizontal layout, so I want to see if I've kind of like composed everything in a way where you can easily see the screen without having to zoom in at all. So let's take a look at this, and yeah, that looks pretty good. Like I can see the source code even in this. I have a pretty small monitor, but even in this small monitor, it looks like I can make out everything. I got the file name in the upper right hand, in the upper left hand corner. I have the shader. I got the large text telling us where the source code URL is. I think that looks pretty good. I think we're gonna go with that. Some of the cropping could be a little bit better, but I think it's good enough for now. Let's see. So we have. I do need to remember. Do need to worry about going over the line. So we have up to line 37 here. So I guess I'll just have to be careful about keeping everything on screen, but I'll also post the source code at tinyurl.com every time I update the shader. So let's close that, and I guess I can keep that there, and I'll keep that highlighted. And let's see. Okay, so I think we're good. So I'm just gonna take this, and we're gonna put this up here. So after we get the Ray March set up, what we want to do after that is, there's a few things I would like to do. I would like to do, okay, so we're going to do Ray Marching setup, and the next thing we're going to do is we're going to do a SmoothMin merge between two spheres that are rendering using SDF sign distance functions. Using Ray Marching. Okay. Alright, everything looks good. Let's begin. So first thing I'm going to do is I'm going to take the shader code from shadertoy.com, and I'm just going to paste it over here. And I am going to keep the, the links and stuff at the top of the file so that other people can look at it. And let's take this main image and let's normalize these coordinates so that the fragment coordinate ends up in the center of the screen. So we're just going to take fragment coordinate and we're going to minus 0.5 times I resolution dot bxy. And then after we do that, instead of dividing by x or y, we're going to divide both sides by, I believe, y works. I think y will get everything in there. So let's take a look at that, and let's also just kind of remove some of these comments. Okay, so that looks... So I'm going to save this. Going to move it over here. And I'm going to take it for a run. And I see that, alright, that's still working for us. Also, every time I do that, I am going to edit what is on PasteBin. So every time I paste back to ShaderToy, I'm going to try to edit it on PasteBin as well. So I'm going to take what we have, and I'm going to save those changes to the PasteBin post so that you can see them on the PasteBin URL right here. You'll be able to see them right here. So this URL goes to PasteBin, tinyurl.com/sdf-004. So with that, you should have this gradient. Shouldn't look much different than what we had before. We're just trying to get the 0, 0 into the middle of the screen. Now, to get a better visualization of that, I want to use something a little bit simpler. I want to use the length of the UV coordinate of UV, and we have to remember that length of the UV is going to... I don't know if length works with 3 dimensions, and even if it doesn't, let's we need to do like a vec3 and then a vec2. Vec2 length. And so it's going to take the length. Length is a scalar value, and it's going to duplicate that value twice into a vec2 to get us the x and y values. And then for the z value, since we're just doing 2D right now, we're just going to keep that at 1.0. And we're going to see how that looks. So I'm going to take that, and I'm going to copy it, paste it over into the shader, and give that a run and see what we got. Okay, so we have kind of like this blue and white, and does that make sense to us? Have we screwed anything up? So we got R, G, and B for our color, and right now I realize that blue is always at... maximum intensity, which I think is confusing, so we should take blue, make that 0. This right here is our alpha value for the color. Let's take that and put that into ShaderToy and see what we got from there. Okay, so that's a little bit better. Notice that everything is kind of like yellow, and we have yellow because the first 2 channels are going to be red and green, and red and green makes yellow. Now, if we want to make this maybe a little bit less confusing, we might want to decondense this line just to make it less confusing. So the syntax up here, I'm going to take this syntax, and I am going to show you what that would look like if we kind of like expand that and don't use as much shorthand. So really all we are doing is we're taking this length right here. So float len equals length UV, and we're taking that length and we're going len, right? Because we got the vec2 here, and then we have this 0, 0. And then right here, you'll notice that we take the color and we tack on another component. So we'll probably make that a little bit simpler as well. But first, we'll just take this and show you that the code does not actually change. So this color right here and this color are the same exact thing. And I just want to show you that. So I'm going to comment this one out. And then I'm going to just take all this, copy it, and paste it into Shader Toy. And we're going to see what that looks like. Okay, so there was no change. If you didn't notice that, no change. Because, well, like I said, it's the same stuff. Now, what we're going to do is we're just going to clean this up. And we're going to take... we're going to take this and kind of make it a little bit simpler. So what I'm going to do is I'm going to take this color and I'm just going to, for now, I'm going to just remove it. So I'm going to put it over here. I'm going to take this, turn it into a vec4, and then I'm going to do 0.1. So this is exactly the same code as before, so nothing is going to change. So I'm going to take all this code, copy it, paste it into Shader Toy again, and I'm going to rerun it. So if you haven't noticed, when I paste it, I'm still on the window where this shader is. I'm just scrolled down here, lower on the page, and all I'm doing is I'm taking everything, I'm going Control A, I'm going Control V, and then I'm just hitting the compile button right here to recompile. So I'm not going to scroll down to show you that because I have the code over here. But if you notice, there is still no change, so let's keep on going. So this is a little bit more explicit. I like it like this. And now we can get rid of this yellow. Let's say red, green, blue, and then why do I have 0.1? Sorry, this should be 1.0 for alpha. It probably didn't make a difference, but let's take that, and now we should have a red gradient. Okay, red gradient, right? So the distance from the center, where the UV is 0, 0, is where it's black, and then the UVs are going negative over here, and they're going positive over here. And then I believe, because this is OpenGL, probably up is where the UVs are going positive, and then down is where the UVs are going negative. So this is nicely normalized. Now we might want to divide by x rather than y, and you'll see what happens. So if we take that and give it a run, right, we're kind of like zoomed in more. So I believe by dividing by x, we get the full range of we get the full range for the x values, but we don't get the full range for the y. So dividing by y, we get a better view of all the values that we're working with. I think that's kind of how it works. I honestly, because I think, like, now that we've divided by y here, on the x-axis here, some of this red is, like, out of bounds, like it's less than -1 over here, and it's greater than +1 over here. But that's just, I think, I could be wrong here, because then why is this not completely red over here? Anyways, I don't know. This is decent cropping as far as I'm concerned, so we're just going to stick with it, keep on going. Okay. So let's calculate, let's create a ray march function. So void march, I'm going to call it SDF march. And we need the origin, and we could call it the camera origin, and then we have another vec3, which is the ray direction. Okay? And we want to march along this ray until we hit geometry in the scene. That's basically what we want to do. So for int I equals 0, I is less than or equal to max steps, and then I plus plus. And we'll have a current origin. So cur origin equals the camera origin. The camera origin multiplied by the current distance. Plus the current distance times the ray direction. So this is, right here, this line is using point normal form to move along a ray. This ray, a certain amount of distance from the ray's origin. So the camera origin is the ray's origin, and this is the ray's direction. So, you know, do we want to call this ray origin instead of camera origin, right, to be more consistent? Yeah, maybe, but I want to name this the same variable name as what I'm going to use in this block of code here, so it's just easier to follow, and that's kind of why I'm doing it that way. Okay, so let's define max steps up here. So we do define max steps, and we'll make it 100, and also I know I need surface distance, and that is 0.02, and then we need, this is also, you could think of this as min dist, and we can make a comment, this is surf dist, and then we also have define max dist, and this will be 100.0 because it's a float value. Okay, now let's SDF March should really return, I think it should return an actual color value. I think that inside the marching function, we'll also have the get light function as well. Like, we'll do the marching, and then we'll do the lighting function as well. So you might want to call it, I might want to call it SDF render, and then we'll take vec3, and we're just going to ray march. So over here we're going to ray march, and then over here we are going to end the ray marching section. And actually, for a section, I usually like to use a little bit thinner of a line, just so that there's a line hierarchy. So I just like to denote things like this, so I know absolutely where the start and the end of the section are. That could be possibly a little bit verbose for people, but that's just the way I like to do it. Okay, so we have a current distance, and then we have a float all distance. Okay? The current distance starts at 0 because we start at the camera origin, and the all distance is you know, we'll call this cam distance, and we'll call this current distance. Yeah, let's do that. So the camera distance, we have the camera origin, and then we have the distance from the camera, and then the You know what? We'll call it pop for point on path. And vec3 technically it starts off at cam org and point on path, right? Okay, so that way we have, I think that makes more sense, the camera origin, the distance from the origin. You know what, let's just make it shorter. We're gonna call this DFC, distance from camera. DFC, distance from camera, point on path. So we're gonna go in ray direction for distance from camera to get the new point on path. Okay, you know what? I like that. That works for me. Okay, so the distance, the current distance, so this is distance from this is the distance from the point on path, and this is the distance from camera. And so rather than name it DFP and DFC, that looks a little hard to visually parse for me. DFP and DFC, they look too similar. So I'm going to add an underscore like that, and that way D and DP like this and DFC, they look different enough where when I'm trying to visually look at the code, I can easily see the difference. So distance from point on path equals SDF, and we're gonna call it we'll call it SDF scene, and this gives us the distance from any point in the scene to the geometry. Now we could say scene geom, because it's obviously colliding with the geometry. Or we could call it distance to nearest we could call it distance to nearest object if you want to be like that. Maybe that would be a little bit easier. So I've seen vec3 SDF distance to nearest object, and then vec3 we're going to use point on path. Yeah, so I want to keep kind of the same variable names. If I call a function only in one place, I try to keep the same variable name. So like when I double click POP, I can see POP kind of like highlighted in all of the sections where I'm using it in that code. So distance to nearest object is going to return a vec3. So how are we going to get the distance to the nearest object? Well, first of all, we need some type of object. So I'm going to have two spheres, vec4 sphere, I'm going to call it object1 equals vec4, and I'm going to call it 0, 0, 0 is the origin, and then it has a radius of 1. And I want two objects. So object 2 also has a radius of 1. And we'll just move them by their radius in two different directions on the x-axis. So that way they're kind of like tangenting each other. We'll make some room over here so that the radius is... the radius component is w. So x, y, z, and w. W is radius. I named these object just because maybe I want a box later, and I just want the code as uniform as possible. So, float, and we'll call this, DST, or we'll call it distance 1 equals a vector from, well, actually, it doesn't really matter which order, but we need the point on the path to the object. So minus obj dot xyz. And then that'll give us the distance to the center of the sphere, and then we need to subtract the radius, so obj dot w, like that. That'll give us the first distance, and the second distance is the same exact thing, except one is object 1 and the other is object 2. So object 1, object 2. Okay. So now let's decide which object we're closer to. So to make sure that your ray marching doesn't accidentally step into an object or step through an object, we want to always be conservative in our estimates for the distance to the scene. So distance to nearest object could also be seen as aka SDF scene. So some people might call this function SDF scene. So I could put a little comment above that for what people sometimes call this function. Okay, so from here we're just going to return the min of distance 1 and distance 2. We'll obviously have to come up with something a little bit more clever once we get like a whole bunch of objects, but for only 2 this should work. Okay. So with that, we have the distance to the nearest object. Once we have the distance to the nearest object, then we can do some comparisons here. And so if the distance to the nearest object is less than or equal to the min distance here, then we're close enough to the object that we should break out of this loop. Like, we've collided with the geometry, basically. Now, if the distance from the camera is too great, we also want to exit. So this right here, the distance from the camera. Now, if something's too far away, it wouldn't be renderable. Also, we don't just want to keep on shooting out into infinity, right? Like, if we're ray marching and we don't collide with anything, we're just going to keep on going, keep on going, keep on going, and eventually we have to just stop it somewhere. So, so if this is greater than or equal to max dist, then we'll also break. So 2 conditions for breaking out of this loop. Okay. Now, if we don't break out of the loop, then we need distance from camera equals the, we can do a plus equal, but actually no, we'll just do, just to be more explicit. So the distance from the camera initially starts at 0, and then we tack on the current distance to the nearest object. And then the next time we do this, the point on the path, right, is going to be that distance from the camera, and then we keep on iteratively doing this and marching this point on path along this ray direction until we get to dp is less than or equal to min distance, where we're colliding with the geometry, or we just march way too far off into space and we just give up. Okay, so now we have to think about, for DP and DFC, are we incrementing these in the right place? Like, would it make more sense? Should we put this here before this condition, or should it come after, right? These off by one errors are always kind of hard to figure out, but let's think about it for a little bit. So the distance, so I'd say for the distance from the point on path, this is kind of like we're looking at where we've currently marched to. That makes sense. So I'd say, and this is also kind of a current value. It's saying where we've currently marched to, like how much are we closing in here? In this current iteration, how much have we closed in, and how far have we traveled total so far? Like, what's our total distance from that camera? So I would say they should actually be both updated here, like this, because let me think about this. Nope. Okay. Okay, so down here. So the point on path, this is the current point on path. We have not edited it. And this point on path is also going to directly correlate to this distance from the point on path. And this distance from... Oh, no, okay, yeah, it definitely belongs here. Because we've incremented distance from camera, but we used this distance from camera to get this. So these calculations will all kind of like agree with each other. What I don't want is I don't want like an off by one error where the like if we put this over here, what happens is this distance from the distance from camera used here in this first iteration is going to be 0, as if it hadn't moved at all, even though we already did this here. Hold on. Actually, I think I like it like... Okay, well, the first value is going to be 0, so it's kind of pointless to calculate this at the beginning of the loop, because the distance from camera starts off at 0. So who cares, right? So we want a... Now that actually could make sense, because we could have a situation where the camera starts off intersecting geometry, and that would create some problems for us, wouldn't it? So since the camera can start off intersecting geometry, I think we need to start off with Um, okay, yeah, I think I'm satisfied with this order. Um, so we're gonna get the um, distance to the point on path. The point on path currently is the camera origin, right? They're coincidental. From there, we're going to take the distance from camera and we're going to like accumulate whatever values we've collected from the distance from point on path. And well, hold on. When we bail out of here, when we bail out of this loop, it's critical that the point on path is actually the correct point on path, and this would make that off by 1. So when we bail out, we actually want the correct point on path. We also want the correct distance as well. So off by 1 errors are kind of hard. Okay. So if we bail out here, is the state of DFC, DP, and POP, do they all agree with each other? They don't want them to be off by 1. I want them all to agree with each other, right? That's basically why I'm trying to like shuffle this around and make sure everything kind of makes sense. So if we start here, we start intersecting geometry, like the camera origin just starts inside the geometry. This would be 0, right? The point on path would end up being camera origin. That's good. The distance from the point, we're saying that we already started like on the geometry. This would be 0. So it would hit min distance. We would exit. We would never increment this. It wouldn't matter because it would be a 0. Now let's say the geometry is like 1 step in front of us. The point on path is going to be the point on path is going to be we're going to update the point on path, and then we're going to find the distance to the point, and then we're going to break out. I see. So if we get too close, like if it's 1 step to this point on the path, this is getting the distance to the surface. So we're not actually on the surface. It's saying that, you know, if it's 1 step to the surface, then I would really like it to be on that surface. So what I'm going to do is I'm going to be a little bit less naive here, and we're going to make sure that the point on path is going to be Yeah, I don't know why this is taking me so long. So distance to nearest object. Okay, yeah, we're just gonna, this is dirtier, but, bail out, and we'll call this one keep going. And the reason why we're going to do it this way is just because obviously I'm having trouble with this like off by one error problem and making sure that the state correctly reflects, what we're doing here. So we have this point on path that we want to see how close it is, right? And this distance, let's say we get really close. Let's forget about this case. I'm not worried about what happens when we bail out with this case. We just need to know that that's there. Um, so So what I'm going to do is time is it? Taking 40 minutes just to decide this. This is horrible. so I don't have any trouble with this duplication here. I think that might make things clear. Um, right? Okay, that makes sense, because here we're going to call this and call this, and this continues the order. If we don't bail out, we call this, and then we still call this, right? So we're going 1 and 2, right? So call this, blue orange, and blue orange. So we're continuing the same consistency, but we're always leaving off with updating the distance from the camera and also updating the point on path. And then okay, yeah, so we're just gonna have to not worry about being off by 1 or whatever. It really won't really make much of a difference anyways, even though I'm obsessing over it. So exit condition. So we could say that these are our exit conditions right here. And we can kind of like do that. So we know this section right here is exit conditions. Right here is our marching loop. Okay, so this is kind of the breakdown of what we've got here for this function here, SDF render. So let's see if we can get that up at the top there. So obviously we're getting kind of big here. So I'm going to keep on coding, and then I know that I'm kind of like going off. I'm going to end up going off screen here. Which that might be. See, how many lines do I have actually on screen? So I have like up to line 61 on screen, but my monitor goes all the way down to line 85. So it's not too bad, but you know, that could be kind of bad. How could I fix that? I don't know. Let's just try to do this. Let's not be perfect. Okay. So once we have whether or not we've hit or not, we're just gonna call float hit equals the distance from the point on path right here. This is going to be the distance from the point on path, and it's going to be like a 1.0 minus. Because if we close in and the distance is like really close to 0, then we want that to be like kind of like full intensity, like a 1. And then if we don't collide with anything, the distance approaches like a very large value, and we want that to end up being 0. So what we're going to do is we're going to clamp this. So this distance, we're going to clamp it to, we're going to clamp the ceiling. To clamp the ceiling, we got to use the min function and 1.0, and then this. So here we've clamped DP to 1 on the top bound, and to clamp the bottom bound we use max, and we'll use 0. So the maximum value is okay, like that. So if dp is like a really high, infinitely high value, then we take the min of 1 in dp, and it's going to clamp the ceiling, right? And then max 0 is because if we have this ending up being a negative value, then the max 0, 0 is greater than a negative value, so this max 0 is going to clamp that at 0. So that's how we're going to clamp it. And then it's the same thing, right? We're going to subtract it here. We're going to flip it around, but we just have this capping value here. Now we could just do this where we say float, and this was the dp bounded. We could call it dp bounded, and we could that way it's a little bit easier to know what we're doing. And so this is hit. So hit equals 1.0 for right, so the hit value is going to be 1 for intersecting scene geometry, and then it's going to be 0.0 for missing scene geometry. Okay, so that looks good. Now, we notice that SDF render returns a vec3. There is a reason for that. So for right now, we're just going to say return vec3 and hit like that, okay? And then we'll do SDF render. We got to call that somewhere. So right now we're kind of doing this. Let's just make sure this all works. So I'm going to take this. We shouldn't see any changes because we just wrote the function, but we want to make sure we don't have any syntax errors or whatnot. And I made a lot of mistakes. So let's go up here and kind of address some of the mistakes I've made. So first of all, I forgot to name these objects 1 and 2 here. And then let's go over to where I'm declaring some floats. Where I declare floats, we got to do 0.0 like that in order for them to be floats. And let's just give that another run, see what other problems we have. Okay, so I still have some more problems. And I can kind of show you. Let's just kind of move this so you can see what kind of problems I'm having. We have a dimension mismatch. Assign cannot convert from high 3 component vector float to high p float. So that's just telling me somewhere I'm using the wrong things. So let's see, is that above the problem or below the problem? I don't actually know. So dp min dist is a float, and max dist is also a float. So I think that's good. Distance from nearest object takes a point on path. And that's also what I expect it to be. Distance, okay, so equal dimension mismatch assign cannot convert from high 3 component vector float to high p float. So it's saying that I can't convert a vector into a float. So I'm going to guess that distance to nearest object, yeah, that's my mistake. Distance from nearest object needs to actually be a float value, and even these distances are float values. So let's take all that and let's paste it in here and recompile. Okay, so now we got green, so we're good again. I'm gonna take this. I'm gonna put it into the paste bin as well. So I'm going to edit my paste bin URL. And I'm just going to copy paste it into paste bin as well. And then I'm just going to hit save changes. And that will be at tinyurl.com/sdf-004 will get you to the paste bin of this code. Okay, so really we don't got much yet. We just don't have any syntax errors. So with SDF render, we need to call it somehow. And right now we kind of have this kind of like very simple rendering algorithm thing. Let's comment that out. And let's create kind of a camera model here. So we're going to do SDF render. And we need the frag color is going to be... The frag color will be SDF render with... we'll call it iRay. Let me think about it. When we are calculating the intersections, we don't just need the ray, we also need the camera origin. So I'm going to use cam origin ray direction. I'm going to use the same thing down here. So it's really easy to see the connection. So camera origin and ray direction, and then we're going to do alpha 100% like that. So the SDF render is returns RGB value, and then we just would need to mask it off with 100% alpha. So, and also, it's not a function like that, so let's just put it equal there like that. And what is the camera origin? So, vec3 cam origin equals vec3, and it's going to be at 0, 0, let's say 9, and this is like a Z up kind of camera model where we're kind of like looking down on the world. Think about like Zelda for like Super Nintendo, where you're kind of like looking down on the character, or any kind of like RPG side scroller. Think of the ground as having X and Y, and then the sky being your Z value. That's kind of the camera model we're going for. And from the camera, we need to like penetrate through the screen we got to figure out which pixel we're rendering, and we also have to figure out the ray direction for that pixel. So to do that, we need to place like a screen in front of the camera, and that's going to be like I think of the screen as like the CRT in front of the camera. So I'm going to say vec3 we could call it glass D for glass distance in front of the camera. Or we could call it yeah, I'm going to call it glass D, just because I try to keep all my variables to 3 or 7 letters, just because I'm OCD with lining things up. So, so this is going to be like a piece of glass that is in front of the camera. And we'll say that it is like a 3.0 units. I'm going to say that there's this piece of glass that's 3 units in front of the camera origin. Okay, so now to calculate the ray direction, I'm going to say vec3 ray direction equals we want a vector that goes from the from a cell on the glass to the camera origin, or it needs to go from the camera origin to a cell on the glass. So we need to figure out what that cell on the glass is. So we're going to do glass cell And the glass cell is going to be, um, since this camera is just looking straight down, the glass cell is going to be uv.x, uv.y, and then it's going to be the camera origin and how far in front of the camera that the glass is. The glass is 3 units in front of the camera, but remember, we're looking down on the world, so we're going to subtract to get that. So, so this is the glass cell. So this is, or you could call this like the pixel cell. So we could make a little listing of what these variables are. So camera origin is origin. Okay. So the camera origin and the glass D is glass's distance in front of camera. And then glass C, okay, so this is we have this screen in our world space, and this is the cell position of the phosphoric cell on that CRT monitor that we're currently rendering. So this cell position in 3D space is going to map to this UV, X, and Y on our screen, but this cell is actually a 3-dimensional position because it's somewhere in relationship to the camera, right? So since the camera origin is up above the world and we have Z up, then to get the glass in front of the camera, we got to minus that. So that looks good to me. We got these descriptions of what these variables are. And let's continue. So to create an array from the origin to the glass cell, we need to subtract them in the opposite order. And I think of it as reading it backwards. So this is cam orig. This is an arrow going right to left to the glass. So from the camera to the glass gives us our ray direction. So we can say ray dir right here. Ray dir is camera to the... Okay. So with that, I think we have kind of like a decent model where I think I have set up everything correctly. We're going to find out. So let's save this. And we'll paste it into Shader Toy, see if we made any mistakes. So I have a dimension mismatch in here. And if we look at it, we can see that cannot assign from float to a vec4, it looks like. So somewhere I'm mismatching float and vec4. So we know it's right here. And frag color, I thought frag color was a vec4. Yeah, it is a vec4, but I forgot the constructor is what I forgot. So we need a vec4 constructor. And then for the first parameter, it is SDF render, which is a vec3, right? A vec3. We combine it with this float value to get a vec4, and then we'll have that frag color. So let's take that, and let's paste it back in here. Give it a run. Everything is green. Let's scroll up and see what we have. So we have a completely black screen. So that sucks, because it's like, what do we do wrong? And because I've screwed this up so many times, I know exactly what I did wrong. Right here, we need to normalize. We have the vector, and this has the correct direction, but we need to normalize it so that it's a unit vector. Because if we don't use a unit vector for ray dir, then ray dir in this point normal form right here is not going to work. because we want to take this as a direction, and it needs a magnitude of 1, so that when we multiply it by the distance, it goes the correct distance along the path. If we don't normalize it, then usually what happens is that this vector is a lot larger than 1, and then this ends up being a lot larger of a distance along the ray than we initially wanted. So let's take that, and I think that's all we need to do, because I think I've screwed this up enough times that I should be able to just run it and know what's going on here. So I'm going to take that all, I'm going to paste it into Shader Toy, and okay, everything went green again, so that's good. But the screen is still black, so that's like, why? Well, let's take a look. We got uv.x, uv.y, we got the camera origin. So what could be wrong here? So the first thing is let's just do some really basic troubleshooting, where we just do some sanity checks, right? So for the SDF render, we're just gonna return vec3 and 1.0, right? Just to see, do just a little sanity check, you know? So we're going to take that, and we'll paste it in here. Okay, so sanity check passes. When we make that all white, it returns, you know, kind of what we thought. So that kind of tells me that you know, it's probably not this, it's probably the marching here somewhere. And I'm gonna guess that maybe it is a mistake here. So let's look at the point on path. I mean, that looks good to me. The length, and we're always returning the minimum distance. This is x, this is y, this is a radius of 1. So I'd say this looks good. I think it's probably the ray marching algorithm. Yeah, so I think it's this, but I don't know. I don't know why. So there also could be maybe something wrong with my camera origin. So I guess what I can do really quick is we can look at some old code. We can look at this previous one I wrote and kind of look at kind of like, how did we do that? Where have we screwed up? So the origin, we're creating this. That direction makes sense. We're doing an SDF march. Curlen, all len is greater than max len. All len plus equals curlen. Yeah, so I don't know why what I've screwed up here. Let's look at the SDF scene. Or not SDF scene. Okay, we're moving so the objects, right? We have X, Y, and Z here, and then 1 for the radius. And we're going to subtract the current origin, and then we're minus W, and then we do the minimum. So I don't think that we have point on path here. And we're doing it in the opposite order. I don't think that should matter, because I don't think... Because I think length should not... Well, let's just see if that... I don't think that should do anything, but let's just... we might as well just try. And... that turned black. Let me make sure that's not, because I think that's doesn't matter, though. Okay. No, we're just back where we started. So we can say that, you know, maybe we want the vector to go from point on path to the object, just because that might make more sense to us. Even though this order doesn't matter here, and then minus the radius values. So that looks good to me. The only thing I can think of is that I have screwed up the ray marching algorithm, and so what we can do for that is we can take this kind of algorithm here, and we could take this and kind of like fill it out again. So we got way too complicated here. So maybe in my getting too complicated, I screwed something up. So the current origin is cam origin and current origin are the same thing. So current origin is going to be the oh no, that's not the... No, this is point on path. So current origin here is point on path, and orig is the camera origin. And the current length, right, it says SDF scene. So this is the distance... all len is going to be the distance from the camera. Okay, so let's see if this algorithm matches. DFC plus equal DP right there. So this looks pretty much the same. Also, we're not going to call this SDF scene. It's SDF distance to nearest object is what we called it now. And this dir is radar. Okay, so with that, okay, and then hit is... Ooh, do we not use a float value? Nope, I think we're good there. DP bounded, float. Okay, so let's save that and just see if that sanity, if we screwed something up in the ray marching and see what we get. So min len and max len still need to be changed because I said min dist and max dist. So min dist and max dist. Okay, so let's give that a shot. And I kind of screwed this up because I still need to put this in the in a loop. Okay. Okay, so that is so that still is working. You know what I am going to do, though? I'm going to say minlen and maxlen and max STP for steps. And just because I'm a little bit OCD about how I do things. So we're going to say I do like, actually, the minlen, maxlen, okay, we'll make sure that still works. Well, works as in, you know, no errors. So there's still no errors, but we still have a black screen. So it's like, you know, I've written this. This is my 4th time doing this, so you think by now, like, I wouldn't screw it up. But I would say that SDF render, I'm pretty confident that SDF render is working correctly. So the question is, then why is it not working? So let's look at the old code, and where is our camera in the old code? So we have the origin of the camera is 9 above again, and this we're doing like a relative, like this phosphor is phosphor.z. Oh, wait, hold on. How does that make any sense? X, Y, and then it's like a vec3 here. Okay, how did that even happen? So that makes no sense to me. This is a vec3. This is a vec3. 1 component, 2 component, 3 component? Like, how is that even allowed? Yeah, that doesn't make sense. No wonder. So let's try to put a vec3 on that. Well, actually, camera origin is 3-dimensional. Yeah, so that makes no sense. I have no clue why that even compiled. So let's just... Okay, so that is a little bit better. Yeah, I don't know how that even let me do that. What? How is that even valid? How is this even valid syntax here? Like, X... You know... Like, I don't know why this is considered valid syntax. That makes no sense to me. So, with that, we kind of know what's going on. I'm pretty sure I'm where I need to fix it now. So this glass that's in front of the camera, uv.x, uv.y, and then it's the camera origin. It just needs, for this z, it's camera origin.z, and then minus the glass distance. So that's really what we want there. So I'm going to save that, Control A, Control Copy. I'm going to paste that into Shader Toy. And I don't expect it to actually be any different. Oh, yeah. Okay, so when I do this, cam origin, now all of a sudden it's a syntax error. I don't know why, but yeah, this should be right there like that. Okay, so let's try that. Okay, so that's kind of like what I expected. So we're good there. That is what I expected. So, for the next criteria, like what we're working on next, so we'll say done. And then, so really what we have is we have done, doing, and next. So what we're doing right now is we need to figure out the lighting. So we need to figure out lighting calculations. And then we'll get into SmoothMin merge. So this is what we're doing now, because we got that working. And before I'm going to take a break. So what I'm going to do is I'm going to take this right here, and I'm going to edit the paste bin for this again. So I'm going to edit it. And then I'm just going to go Control A, just paste that all directly in there. And then I'm going to update it. So I'm going to save those changes. And then I'm also going to make absolutely sure that this tiny URL kind of like goes to what I think it goes to. So I'm going to open up Torch browser really quick. And I'm going to move this back to... Okay, so let's... I'm just testing out the link right now. I'm making sure that that works. Okay, so that still works. Like, I don't know if you'll be able to see here, but, oh, god damn it. Because I kind of cropped a lot of this, so let's see if we can just go over here. Can we just put it over here? So yeah, on paste bin, that is kind of working for us. I'm seeing it on paste bin. So all you have to do for that, if you want to see the code on paste bin, just go to this URL right here, tinyurl.com/stf-004. And right now I want to take a break. So what I'm gonna do is I'm gonna set like a timer for like 8 minutes, and I'll be back after that 8 minutes. So let's see. See if we can do a. Let's see if we can get like a countdown timer that looks decent. So I'll just make a little note here. We'll close this, and we'll just say like that's not really large enough. So I need... So that looks good for that. So I am just right now, since this is my first time to actually try to make an organized stream, there's a little bit of chaos here where I don't know what I'm doing, and I need to like, I need the screen to be kind of like presentable. So this is my attempt. I'm gonna just make an attempt to make like a little banner that kind of says what's up. So let's how am I going to do that? So if I take a snip of the current screen, Okay. So I'm just still editing, in the process of editing here, to make some type of decent kind of display. Okay, and let's see, we will... Right. Okay. Let's edit that background, make the background a little bit better. So we will do... All right. Okay, so let's see if I have a decent thing going on here. So that's kind of good, except it's in need of some cropping, and so I would like to kind of like make things as nice as possible here. So let's work on some of that presentation here. So we got these different sources. I'm gonna create another source for the break in OBS. So I'm gonna add a new source. And it's going to be a display capture. And we'll do add a new source. Okay, so it's going to be a break screen on the left monitor. Okay. And now the next thing I want to do is I just want to take how it looks like in the photos and I just want to crop that. So I'm going to add a filter. And we're going to apply a crop / pad filter to this display. And now we're just going to start cropping the display so that we don't have any of those weird looking edges where it's kind of like just looks a lot better. So left, and then the right, we'll crop that a little bit. Okay. So that looks good. And then the top, we'll crop that. Let's just put it in a 50 really quick. Let's put in an 80. Let's put in a 90. 120. 110. 120, yeah. 120 works. And then for the bottom, let's just put in like 20 maybe. And I would say that works. So let's do that. Done. And now the next part is, because it's been cropped, it kind of doesn't, it kind of like leaks a little bit. So we're gonna, or actually it's, let's hide this. Okay, so now that we've hidden that, we can kind of Okay, so that looks good to me. Actually, you know what? If we could just move that up a little bit so that it kind of like lines up. Can we use arrow keys here? Yeah. Okay, so if I use the arrow keys, okay. So that looks... Okay, so that's nice and aligned. I like that. So I'm gonna take my break screen, I'm gonna lock that. And then when we have we're looking at our code screen still looks good to where okay, it could use some work. It could still use some work, but I think that looks decent. I can look over the stream later and figure out what parts I don't like. But I'd say that all looks good. So I'm gonna lock these because they're it's a decent layout so far. Um, oh, I see. So we need a little bit of padding here because depending on where I'm scrolled, things can kind of get a little bit things can get a little bit oh, yeah, so that's a problem. Um so let's we're gonna have to edit this a little bit. Okay, I think that is good enough for now. And I just have to remember that okay. Okay, so that looks good. As far as like organizing the screen a little bit. Um, so with that, I'm gonna go over to my break screen. I'm gonna lock all of these compositions, and then I'm gonna hide the break screen, and yeah, okay, that looks good to me. Um, so I'm gonna take a break. And how long have we been going? We've almost been going 2 hours, and I haven't even gotten back to. I've been going slower this time just because trying to get organized. But I think this looks nice. So we got the break time. We got what we're doing next, lighting calculations. So yeah, let's just set that timer, and I'll be back when that hits 0. Oh man, right on time. Okay. We can clear that, go back here, and we can minimize the break screen. We can close that, and we can hide the break screen. Yeah. So we want to see what files open. We want to see the lines. Okay. So we're on to figuring out these lighting calculations. So let's go over into our code. The first thing is I wonder if, before I do that, let's see if this other code that I wrote also works, or if I was just mistaken. I'm pretty sure we'll get like the same result. So running that, I actually get a problem. I get like a line in the middle of it. So why is that? Yeah, I don't know why this is wrong, but this is wrong. I don't know why it's wrong. Let's just let's just use this because we're overthinking it anyways, and this works. So let's just take that. We just got rid of all that other code just because it was very cluttered. Okay, so there we go. Good enough for me. Let's continue. So where we have this, we want to get like a light. So float, we'll say light intensity, Li for light intensity. And light intensity equals SDF. Get light, do you want to... Sure. SDF get light. And what we want is we want the light from the position where we hit the surface of the material. And when we look at this, we see that dp min len, distance from point on path. This is our collision point right here is dp. So we'll take that position and try to figure out the lighting situation for that. Over here, what we'll do is... Now the thing is, with the lighting, we might actually have some reason to eventually return different colors for the light rather than just an intensity. So I think SDF get light might want to return a vec3. And then we'll do a vec3 and we'll use dp, right? And we're using the same variable name as what it's used in the function call, just so that it's easier to like be able to click on the variables and see the relationship between what we're using here. So get light dp, and right now we're just going to return a vec3, and we're just going to do 1.0, 1.0, and 1.0 like that, right? And right down here, we need to actually use that. So instead of returning vec3 hit, we're just going to return a vec3 of the light intensity multiplied by the hit. And if we want to make it kind of obvious that, you know, this is a vector, and this is a scalar. We might want to do dot xyz times hit just to make it a little bit it may be an explicit cast so that we know that the hit is a float and the other part is a vector, right? So just a little bit of like explicitness just to make it a little bit more obvious when we're just reading the line and we're not looking at the when we're not looking at this line in context, we can tell that, oh, hit is a scalar times some type of vector, right? So taking that, let's take that and let's just paste that into ShaderToy and see what we have. I expect no difference. Now I screwed up the getLight function, so getLight takes a vec3 and it returns a vec3. Oh yeah, distance dp is the distance from the point on path, but we actually want the point on path is what we want. So we want point on path, and right, so this is point on path here. Okay, so let's take that and let's see what that looks like. Okay, so that's working again. No difference, no change, which was expected. Okay, so to calculate the lighting situation, we're going to need two vectors. We need the normal vector of the surface and the light vector. So the light vector is pretty simple. Vec3, we're going to call it light vector. And it's going to be the direction from the point to the light source. So vec 3 LP. So we're just going to have one light position equals vec3. And we'll put it at like I would like it where the camera is, and then move it around a little bit. So the camera origin is at 0, and then it's like up 9. So I would like to just put the light at initially at 0, 0, 9 like that. But then I want to add some offsets plus vec3, and we'll do we just want to move it on the x and y. So cos of I time multiplied by some type of radius, let's say 6, or I don't know, let's not worry too much about the exact radius, sine I time, and right, we're doing a parametric circle formula right here, right? So the cosine and sine to create a circle, and we're gonna take the angle right here. So the angle is going to be based on I time multiplied by 6 point. That's wrong. So we want to take the angle and we want to multiply the angle by 6, right? So it's a circle with a radius of 6. So this 6 has to be the same on both. If they're not the same, we get an ellipse oriented on the x or y axis, depending on which one's which. So these need to be the same for a circle. And then for the z-axis, we're just going to keep that as a 0, because we're going to keep that z position the same. We just want the light to kind of orbit. That's just going to give us a little bit more visual feedback as to whether or not the lighting situation is correct. So right now, we could do something where we're just LP light position, and then we could do LV light vector, and LN is going to be light normal. Okay, so The light vector is going to be from that point on path to the light. So therefore, we need the light position first, because remember, when we create the vector, we think of it as an arrow going from here to the left. So think of this minus as an arrow pointing to the left. So from the point on the surface, which is noting by point on path, right, we might want to make a note that this right here is also the surface XYZ. And so we have that light vector, and then for optimized code, we might want to not be so verbose like this and make it all in one step. But for readability, so that you kind of know what you're looking at, we have a light vector, but in order to get the light normal, we need to normalize it, right? Okay, so with that, we're going to do the same thing. We're going to do the same thing, but for the normal, for the actual geometry that we've hit. So we need like a surface normal. So light normal. This is the light normal section. And then we can make a surface normal section. Now, it's a little bit tedious to write stuff like this, but I think of the philosophy of code is read many more times than it's written, so I try to keep things organized. So to get the surface normal, we actually need a kind of like a calculation for how we're going to calculate that, and the surface normal calculation is a bit heavy duty, so sometimes I put it in its own function. But this time, I think we'll just do, we'll do it all in the same thing. So just follow with me. So sexy Z are our defines, so those are the variables we're going to be using. And you'll see why. Undef. Okay. And so I'm just going to fill in all the things we need for the formula. So I need distance to nearest object is going to be this S function, so it's like the surface function. E is an epsilon, so we're just going to do like 3 zeros and a 1 after the decimal. And X, Y, and Z are the original point on that surface where we had the collision. So dot X. Okay, so now that we have all of these inputs to the surface normal calculation, what we can do is we can say let's say, where are we going to put this? Vec3 Sn equals still a Vec3, but when we construct it, we have 4 different sections of formulas here. So there's one step forward, 2 steps back, positive and negatives. So we have a positive and a negative section, and it's separated by a minus. And then we have a section that has the X, a section for the Y, and a section for the Z. And so just remembering kind of like how this is constructed kind of like helps me remember the algorithm for calculating the surface normal. Okay, so now that we have this, we need to do a Vec3, or is it a Vec3? Let me think. Yes, it's a vec3, because what we're going to do is we're going to do x. Actually, no, it's, we're going to get the distance. That's going to be x minus e, y, and z, like that. And this is actually our positive one. And then we do the same thing for x, y, and z, but as we change which letter is in focus, we move this e over like this. And I like everything to line up, so it's kind of like obvious what the pattern is in this formula. And so over on this other section, it's the exact same thing, except instead of doing addition, we're going to do minus. So we're going to change all these to minuses. So remember how I said this was the positive, and this was the negative section, and this was a minus? And that's how I'm thinking of it, as one step forward and 2 steps back. And that's just like a little like saying or mnemonic. I don't know if it's a mnemonic. Maybe it's a mnemonic, but it's just like a little saying to help me kind of remember how this formula is constructed. So once we have this vec3, and right, S is the surface distance formula. So that looks like a decent formula for that surface normal. And I'm pretty sure that that is already normalized. We can check some old code of mine really quick. So let's look at the previous one I did and see if I'm doing this correct. So I see that it's normalized here. So I forgot one part, and I called this function snorm. We're just inlining this function in the code that I'm writing right now. Unless I'm going to call it from another place, I think it's better just to inline it, because it makes the flow of the code much easier to read, and also it minimizes the surface area of your code. So now that we know that this needs to be normalized, we'll just do normalize. We'll just do normalize, and then we'll put another thing here. And now that we have the surface normals, we can actually do some calculations with that. So, okay, so it's the same deal. So the light intensity is just going to be vec3 Li equals the dot of, and I don't believe, yeah, it doesn't matter what order the dot is in, because the dot is the angle between two vectors. Or it's not the angle between two vectors, but it analyzes the angle between two vectors, and if they're parallel, it returns a 1, right, for maximum intensity when, like, the light rays are hitting straight on. And then it returns a 0 when the two vectors are perpendicular to each other, or not perpendicular. Okay, let me say that again. When light hits something straight on, then the surface normal and the light vector, they're going to be parallel, right? So the dot product for those two vectors is going to be 1 for a maximum intensity, and those are two parallel vectors. When you have a surface normal that is perpendicular to the light normal, then that surface gets absolutely no illumination, right? And those vectors are perpendicular. And when that happens, dot returns 0. So because we're analyzing an angle between two vectors, I know that the dot product doesn't care about order, right? And then I can deduct from that oh, it's cross that cares about order. Do I remember what cross product does? No, I don't. It's been a long time since I've done linear algebra, but I knew one of them cares about order, and it's definitely not dot product. So with the light normal and the surface normal, using the dot product, we can get the light intensity, and then we can just return that light intensity And if we didn't screw anything up, then we'll have something. And do I think we screwed something up? I absolutely think we screwed something up because I consistently make a mistake somewhere. I wish I was smart enough not to, but I do. So, dimension mismatch in the light intensity section. So, so that makes sense because the dot product returns a scalar. So, so what I'm going to do is I do want the this really should be light color. Light. Or it's not really color because it has RGB. LV for light value is going to be confused with light vector. So I'm going to call it LT for light triplet. I'm going to call it LT for light triplet. And then right here, I'm going to say this is going to be a float. Float light intensity. And then vec3 light tuple equals vec3 and li, and li like that, right? So now we could change the color. Like if this object only reflects red light, then we could just make these 0 and 0, and then we would have a different color in our scene from the light emitted. So that looks good there. Now the problem is that with get light, we got to look at where we're using get light because li, I'm no longer using li. I'm calling it lt for light tuple. Lt light tuple. Okay. Actually, it's not a tuple. It's a triplet. Okay, light triplet. Okay, so that looks good to me. But I'm not going to be surprised when it doesn't work the first time, so let's take a look, see what we screwed up. Macro redefined error. Well, that is... Did not expect that. Yeah, I did not... How the heck? Oh, you know what? Control A... Make sure everything is deleted before I paste it. That's probably a problem. And macro redefined. Really? Macro redefined? You're kidding me, right? Which macros are redefined here? X is redefined. Oh, yeah. So I see. S, E, X, Y, and this is supposed to be a Z. So I even said that that's how we were doing it. I don't know why I forgot the Z. Okay, so save that. Control A, Control copy, Control A, paste. Okay, so what else did we screw up here? Operation result is undefined for the values passed in. Why? Got it. So these functions all take vec3s. So we need to do vec3 like that. And I already knew that's kind of like what I wanted, but I just wasn't paying attention there. So with that, we should be good. But I don't know anymore. That's why I have confidence problems with, like, you know how they say, I don't know what my intelligence level is. Because, you know, they say, like, stupid people are always sure of themselves and smart people aren't. Uh, I guess that's a good excuse for why I'm screwing up. Um, or maybe I just suck. I don't know. Okay, so there we go. So we got our two spheres right next to each other where I expected them, and we got our light. Our light's kind of like up above. Our light is kind of like at the same z height as the camera, and it's kind of like circling around the camera. That is what I would expect for the lighting calculations. So I would say for the lighting calculations, we are done. Now, before I say we're done, I would like just to mess around here. So this light tuple, let's say red, green, and blue. Let's say that it only reflects red light. So let's just make those two 0 like that. And then let's load that into the shader and see if we have like red. Yep. So, right, nothing really fancy. But that's kind of the beginnings of where you would kind of like account for the material rather than just the lighting intensity, like having like a material diffuse color or some type of texture that would somehow plug into this light tuple over here. There's one thing I'm missing before we continue, and I can't quite remember. Oh, yes. So, right now we can see that in the places where there's absolutely no light, we are getting complete black. And that's not quite ideal. So we want to make the light kind of... we want the shaded areas to kind of like... show up, I guess. So let's say that, you know what I'm going to do? I'm going to say that, I'm going to take these variable declarations right here, and I'm going to paste them over here, and we're just going to declare them before we use them so that I can have a little bit of space to think this through. And what we could do is... light in 10... So let's do some trickery here. Let's say that if this light intensity is 0, then if that's 0, if we don't have any light, we're just going to have some fun with this and make kind of like a dark blue kind of like area, just for the fun of it. What did I screw up now? Oh yeah, so dots. You always have to be very explicit with this. Now I don't need 0.0s here because we have the vec3 constructor here, but here you need it. Optionally, we could do like a float 0, which I feel like that's just a little bit hard to read, so a little bit cluttered. I mean, technically, I guess this is clutter as well, but I like putting, well, it's the same amount of clutter, right? Because if we get rid of this, then well, we still need a constructor no matter what. So I feel like this is a whole bunch of clutter. So, and we can omit the decimal places, use vec3, and then we can definitely see the difference between 0 and 0.1. These differences between these three numbers is much more obvious. So when I say reduce clutter, I just mean make it so that when you glance at the code, you can kind of tell what's going on right away without too much analysis. Making things visually sleek will make it so that your brain can just like parse what you're looking at a lot easier, if that makes sense. Okay. So there we go. So now we kind of have, you can kind of see that blue right there. And that kind of helps us know that what part's kind of like in the shade. Doesn't really look very believable though with that different color. So I guess, you know, let's just let's be a little bit less creative here and just make it like a very dark gray color. And it needs to be okay, so obviously that's not dark enough, right? Because now it's kind of like lit up. And we're trying to like just make the... We're just trying to keep the darkest area from going completely black so that we can kind of differentiate it from the background. So, so this is kind of hacky. So it's not really a completely accurate way to do this. We're kind of like faking it just so that we can... We're faking some like global illumination. So really, if we're going to add this, we should probably do like float GI. GI. And then this GI value, what we can do is that, like that. And we can put this GI here, here, and here. And to make it a little bit more obvious what's about to happen, let's say 0 plus GI. A lot of people hate it when I program like this, where I like explicitly put zeros. But now that makes a little bit obvious what's going on here. And what am I missing? Let's take all of this and just paste that, and then we'll paste it again. So basically, to avoid, if this equals 0, we don't know what the darkest, if this equals 0, we don't know what the darkest value is. So if we pop this up by a value when it's black, then we also need to pop this up by a value, the same value, so that it's consistent. You see what I mean? Now with that, if we do it that way though, we don't even need this if statement is unnecessary now. Now we might want to keep this in case we do want to add some special stuff here. So I'm not, even though the if statement right now is unnecessary, I'm gonna keep it like this for now. So let's take all this code and let's paste it in here and see if what did we screw up? So once again, I'm just gonna say 0.0. This is one of the more common mistakes I make. Okay. So take that. Okay, so that's working again. So now the darkest sections are not completely black, but everything is a consistent gradient. Okay, so now we are done with the lighting calculations. And we are on to... We are doing the SmoothMin merge now. Yeah, we're going to do the SmoothMin merge. So right now I would like it so that these spheres kind of blend together when they get close to each other. So before we kind of like try to SmoothMin merge this, we should probably like animate these spheres a little bit so that we can see the difference in how they merge together when they get close to each other. So for objects 1 and 2 right here, which are our spheres, we're just going to like animate them. So we'll do like on the x equals the cos of I time, and then object 2.x equals the sine of I time, and we'll just see kind of like what that looks like, and if we kind of like how that's going. So let's just take a look at that. Okay, so we got them merging together, and so they need to sometimes not be so close to each other. And right now their phases are kind of like, their phases are offset, but they're still synced up to each other, right? Like their phases divide into each other equally. So we need like one to go a little bit faster than the other, so that we can have one of them pass the other sometimes. So I'm just going to do sine times I times 2. We're just take a look at that, see what that looks like. And it's 2.0. Okay. Okay, so now they're still kind of merged together all the time. So let's just keep them both as sine. Simplify that a little bit, and now we should be good. Or not. Oh, no, okay. So a thought is that they do start off tangent, so I don't know. Well, let's look at the math here. Let's try to make a radius of 2. And that will give it a little bit more distance. It'll travel a further space. Okay, so they're apart. Okay, and they're merged a little bit for a while. They're apart. They're apart. Oh, merged a little bit for a while. Okay, so I like that because we get to see what they're like apart. We get to see them merge together really quick and split apart. And then we also get to see them kind of like stuck together for a little bit. And so we'll get to really clearly see the interaction between these two spheres as we try to like merge them together. Okay, awesome. So now the next part is I need to do some graphing. And for that, we're actually going to need to like full screen. We're gonna need to full screen the we're gonna need to get a graphing calculator up, and we're gonna have to do some math. So let's I gotta make some more I need to make some more cameras here. Scene. Yeah, so I'm going to add a source to I'm working with OBS right now. So I am just going to add a display capture. And Add source. I'm going to add a new source. And we're going to say this is bot.fullscreen. Okay, so I've added, this is my entire bottom monitor right now. And I'm going to use this to go on and gonna do some graphing. So we're gonna just take this and we're gonna take the current snapshot of the code really quick, and we're gonna update the paste bin. So I'm gonna go edit this, and I'm just gonna paste everything in there, and then I'm just going to save the changes. And if you need this, the URL is right here. And then also, it's tinyurl.com/sdf-004 if you want to take a look at that. So that looks good to me. So let us continue and go to Desmos. And I've tried this a few times, but I don't always get it right. So we're just going to take two equations and we're going to try to blend them together. So okay, so we have these two equations and we want to kind of blend them together. So if we take, we want to assign these values. So equation A and equation B. And so if we do, Jesus, okay. No, you did -2. So if we want to blend these together, we're going to do like min AB like that. And if we hide the top two equations, we see we got like this blend between these two equations. So the next thing is, how do we, when we're looking at these equations, we notice that the transition from one equation to the other is very sharp, right? And if we are looking at, if we're looking at our situation here with our two spheres, we notice that, well, the transition from one sphere to the other is very sharp as well, because we're doing the min function to figure out which surface we're closest to when we're doing our ray marching. So that all makes sense, but how would we make the surfaces, when they're very close together, kind of like start to blend? And then when the balls are very far away, not have them, the surfaces blend. We want to have like this metaball merging effect. So let's keep on going and see if we can figure that out. So how do we smooth out this graph? Well, the first thing is we need to somehow isolate the points where these transitions are happening. And the quickest way to do that would probably be like a minus b, right? If we minus both functions, then we get 0 at exactly where these transition points are happening, right? So there's a 0 here where this transition happens, and here we have a 0 where this transition happens. which that's great, but when the transition happens, we want our ramping to be like 0.5, right? When we're directly between the border, between the two different graphs, we want 50% of each, right? So what we're going to do is we're going to just add 0.5, 0.5. And now, in the area where this transition happens, where it's right in the middle, where it's on that border, then we have 50%, right? And then where this transition happens as well, we have 50% as well. So now the next part is when we are how are we going to apply a percentage to these graphs to blend them together? First of all, we should probably just figure out, well, how do we blend from one graph to another in the first place? Before we figure out how to do this tricky blend where we have these different weights depending on how close we are, we just need to figure out how do we blend one graph into another. So let's think about that for a second. So linear interpolation would be like a times t plus 0 and plus b times t, 1 minus t. My bad. And then this will be 0 plus t. So obviously you don't need the zeros. I just like to keep things as consistent as possible so that I can identify the patterns in the code a little bit easier. And some people don't like that. That's my habit. I also do weird stuff like bit shifting by 0 as well. Okay, so now that we have that, we can see this kind of thing where when we change the value of t between 0 and 1, right? 0 for 0%, 1 for 1%. So when it is at 0, it's 0% of A, but we invert the percentage here, so it's 100% of B. When we flip this around, we get 100% of A, and then 100% minus 100% is 0, so 0% of B, right? So on the extreme ends, we have 100% of one of them and 0% of the other. When we're in the middle, we have 50% of each. Let's unhide the two functions so we can kind of see how we're blending between them. And let's make both of these functions kind of black, right? Because they're our starting point. We really don't need to know exactly which one is which when we're looking at them. We just kind of need to know that they're the two functions that we're starting with, and we want to blend between them, right? So here's this red line that interpolates, right? So you see how it's kind of matching up to here, and then over here, over there, right? And let's actually make this dashed, because I can't really see it when it's overlaid. So let's make both of these dashed. Okay, so now that they're dashed, I don't know why one's bold. Did I accidentally bold it? Yeah, I don't know why that's bold, but whatever. It's good enough. So right now we can see when it's blended here, we can obviously see the dots in the red line, and when it's blended here, we can see it there as well. So now we have this function where we can obviously blend between it, and now we want something where when we're like over here, we want that t value to be 0. Do we? Hold on. Actually, no. We should probably switch these around. Yeah, let's reorder these functions for a second here. So let's take this function, that function. Okay, so I'm going to swap those functions. I'm going to rename them as well. A and B. Okay, so A and B, and let's make that dashed again. And we want, when this is at 0, we want A to be 100%. And then when we're over here, we want B to be 100%. That's just going to make it easier for us to like visualize this as we're breaking it apart. So for this interpolation, we're going to just do a 1 minus t over here, and then a 0 minus t over here, right? So we're kind of flipping, we're flipping that around. Or hold on. Okay, there we go. So we flip that around, and that just makes it a little bit easier because now when we see A, right, A is on the left side, A is the first one here, and when we're on the left side of the slider, we're latched to A. When we're on the right, we end up at B, and B is the second one, so, and then B is the second one over here. So B is the second thing here, and it's also the second thing here, and it's also on the extreme right here. So that's just making all our things kind of lined up a little bit better so that it's easier to think about things and not make any transposition mistakes as we're trying to like figure this out. So now we know that in order to like blend these shapes so that we get some type of curve that is kind of like this purple curve, but it has kind of like a smooth transition here, we know that at the very beginning, we want this red line to be strictly latched to the first graph of A, and then we want it to smooth out, and then we want it to strictly latch to the graph of B, smooth out again, and then strictly latch to the graph of A again. And so we have to figure out how to manipulate the value of t over time so that that can happen. So now if we do this like this, we might not want to do it backwards like this because, well, yeah, actually, no, this is good because t is going to start at, so in the transition, t is going to start at 0. Like in this general area, we want t to start at 0, ramp up to 1. And is that it? We're missing something here. So actually, no, over here, we want t to be 0. Then when it gets over here, t is 1, and then it goes back down to 0. So how are we going to make a graph that just gives us the correct step inputs? So let's make another graph, and let's do the min AB again. And let's do A minus B. Okay, you know what? If we do A minus B, and then we add 1, so right now it's at 0. It's at 0 where that change is happening, but we want to add 1.0. So now, whenever the graphs are crossing over each other, where there's that transition point, then, so here's a transition point right here, and we see that we have the output being 1 at the transition point. Same thing here. The output is 1 when there is a transition point. And down here is where we want t to be. Over on this side is where we want this segment here. We want t to be 0. This segment in the middle, this green segment in the middle, is where we want t to be 1. And this segment on the right is where we want t to go back down to 0. So what we can do now is we can clamp this graph right here. We can just clamp it between 0 and 1. So we'll do like, we'll say that the max value, well, the max value is going to be min 1 in the graph, and that's going to cap it at 1, and then we're going to cap the ceiling as well. So we're going to do a min 0. I feel like I did something wrong there. Why is our graph? Yeah, that's not what I wanted. What did I do wrong here? So let's back up again and just be like, you know, we were so good, and then we just kind of screwed something up. So let's put more parentheses, first of all. So if we want a cap on the top, we got to use min, and we got to use 1, and that is going to cap the ceiling for us, right? Okay, so that is correct. That looks like how we want it to look. And then it's going to be a max 0. Okay, so I'm not sure where I screwed up earlier, but now we have this kind of transition where well, we do have a problem here where it's crossing over. We have the transition right now is happening not quite where we want it to happen, right? The transition is happening right in the middle here, and we want it to kind of like cross over both. So what we could do is to give it a little bit more transition time, we could to give it more transition time, what we could do is we could change that ceiling. And right now we could change that ceiling to maybe 2. Let's see what happens when we change that to 2. Okay, if we change that ceiling to 2, we get somewhere where on we have to translate this now. So this section over here, we want this section to be ramping to let's think about it. Yeah, this is our transition section, and our transition is going from 0 to 2. So if we just divide this by 2, right? Because we're at 2 and we want to squash this down. So let's take this whole thing and let's just divide it by 2. Okay, so now that we've divided that by 2, we see right here at this transition point, 0.5 at this transition point, right where the graphs are crossing. And then right here where the graphs are crossing, we also see we got like this 0.5 transition point, right? Now the problem is that because we're ramping directly into this green graph you see is basically, we want to replace this slider here with this green graph. So this green graph is eventually going to be our t value. And I just know that if you have jagged inputs are always going to kind of lead to like jagged outputs. So this sharp corner right here means that if we try to blend with a t value that's using this graph as an input, we're not going to get the smooth blends that we want, because the transition points on this graph are still they're still very rough. So we want some way to take this formula we've kind of derived. We still want to smooth out these corners. So I need to go to the bathroom, so I'm gonna just take a break here. So let's hide that. Let's put on our break screen. And okay, so this is what we're trying to do right now. SmoothMin merge. I don't know, I want to make that, what color do we want to make that? Okay, so this is what we're kind of working on right now. And I don't know how long it's going to take me. Let's be generous and say that this is going to take like 15 minutes. Okay, and when I'm back, we're going to keep on trying to derive that graph and figure out how to blend these two functions together to create a smooth min function. Okay, so I will be back when the timer is at 0. Okay. Okay, so in retrospect, I kind of realized that I shouldn't. Um, if I say I'm going to be back in 15 minutes, coming back early isn't really fair to somebody who like set their timer for 15 minutes to like go away and then is ready to come back later. So we're gonna wait till it hits 0 to continue, because I think as far as establishing a format for the stream, we should definitely make it so people, you know, are able to safely walk away from their computer if they want to and come back when they start up. Good stuff. So let's see, do I have any monitor that I can actually use to browse the internet while I wait for this? And I do, it's my top monitor. So I'm gonna go look at memes for a while. And when that hits 0, then I'll be back. I would check Facebook, but I set up a blocker on Facebook, and I'm out of Facebook time for today. I think I get like 15 minutes a day. A lot of times the blocker turns on when I'm like making a comment to a post, but let's be real. Most of the time when I'm commenting on somebody's shit, it's just asking for trouble anyways. So it's like, you know, you're on a political post, you're about to make some type of comment, you're just inviting trouble for yourself, you know. Like, I don't know, man. Politics is bad for business, right? Like, if half of your customers are Republican and half of your customers are Democrat, and they both fucking hate each other's guts, then politics just eliminates half of your consumer base, right? Like if we're like manufacturing cars, okay, politics and your position on different issues has nothing to do with a fucking car, right? So the only thing you do by being political instead of just saying what your car does is you drive away half of your market. So same thing with your friends. Like if you're too political, you could drive away half your friends, which means that you could drive away half of the people who are knowledgeable on things that they could help you with. Now, if you do have to side, like if you're going to be forced to side with one side or the other, you want to side with whoever has the most to offer you. Yes, it's a very sociopathic way to look at it, but we're all trying to survive, right? The imperative of biology is we just want to survive and reproduce, right? And if you want to do what you're meant to do, you need to figure out how to survive. You know, look after yourself first. And then if you have any extra energy, you can look after other people. But first thing is just to look after yourself. So if you do end up having to choose a side between two different groups, which side has the most to offer you? Like if you have to side with one group that has nothing to offer, another group like that's how I would do it. You know, some people might want to just go, I'm going to side with whoever's morally right, but I think siding with speculating on the morality of things is really like a first world issue. It's like we're so rich in this country that, you know, we can spend all this time mentally masturbating and philosophizing on morality. And people in places that aren't doing as well, they don't have that luxury, right? They just got to do, if they have one option that's going to kill them and one option that's going to keep them alive, right? They're not going to worry about the morality of one option over the other. It's, you're sticking with the one that keeps you alive. And, you know, we still have the same thing here, but it's just a little bit more abstract. Like, if you have one option that loses you your job and another option that keeps you your job, well, then you want to keep your job because jobs make money and money gets you food and food keeps you alive, right? But, you know, different people, I don't know, I just think that dying for your opinions is kind of like a very egocentric thing to do. Like, you're so caught up in your ego and your opinions of things that you'd rather spout them off than to save yourself. I don't know. That's just my opinion. So maybe, ironically, I'm spouting off my opinions that I shouldn't be spouting off. I don't know. But that's why I like math. Math is very unambiguous. Like, if we run this code and the code works, there's no debate, right? There's no ambiguity. As far as like our current political climate, like I have no fucking clue what's going on because all of the information sources that I absorb, they're like all contradictory, right? Because I try to, you know, absorb media from all sources, like conservative and liberal, or progressive, if you want to call it progressive, whatever. And everything is so contradictory that I'm clueless as to what's going on. So if you're clueless to what's going on, then I feel like the best option is to do whatever you think is gonna keep you alive, right? If you're clueless as to what's going on in the bigger scheme of pictures, well, at least think about in the microcosm, how can you protect yourself? Anyways, we're about ready. And okay, it's been 15 minutes. So let's get back to it. So let's and I just ranted. I didn't even look at any memes. Okay, so I'm gonna close the break screen, and we're gonna put the, you know, oh, okay. Okay, there we go. So, we have this transition curve. We want to take the value of t from 0 to 1, and we want that ramping to happen where it is at 0.5, right where that transition happens, and then it fades into the transition over this border, right? So here's where we want 50-50. Here we want more. Here we want less. Here we want more, right? So t equals 0.5 here, and then t equals 0, t equals 1. And I've kind of said that multiple times already, but okay, so this curve right here, this green curve, it has very sharp transitions, so we need some formula to kind of soften this curve. And the way we can soften that is we could get some type of curve where, let's take these for a second. Let's try and make another formula. So let's call this I don't really know what to call it. Let's just call it M for now. Is M like a reserved variable? Okay, so we got A, B, and did we already have a C? No, so let's just call this C for now. Okay, what the hell is going on here? Is it because... Okay, there we go. So C, can we just name it M then? Was it just because it was in a bad place? Okay, yeah. So, and then if this equals M, right, we'll just, okay, yeah. Okay, so there, we have that formula. So I kind of remember something like m minus 1 minus m. Now that's not what we want. M minus 1. No. 1 minus m. I'm also kind of paranoid that this m is wrong, so let's... I don't think it is. Oh, I see. Why is that? Okay, so the m is fine. Now it's just that we want to kind of like, we want to turn... We want to turn this green line into like an arc. And for that to happen, we want to take m and we want to minus the... I thought we wanted to minus the inverse. So that... Oh, you know what? No, we don't want to... M is between... M is between 0 and 1 right now, right? Yeah. So if we multiply something between 0 or 1, it will end up between 0 and 1. So I don't want to minus. I want to do something like multiply by... There we go. So now we have something where... Let me look at the other equations here for a second. Is that really how we need to do it? Yeah, I'm not sure. We want a... We want to be able to, like, ramp that in. We want to take the original M curve, and we want to... We want to slowly ramp it into itself. Yeah, I don't know. Feel like we need to like multiply by like a S curve or something. I'm kind of lost right now. But I definitely know we need to like smooth this out somehow. And huh. Well, let's just see what we can, what happens if we like add another equation here, and we just say um, n. So we'll call this n. And what happens if we take m times n, right? Um, so when we take m times n, we definitely get like a nice transition at the beginning, but we still get that sharpness on the bottom, don't we? What if we do m divided by n? M divided by n. M divided by n. And that, oh boy, now we're like way over here. Whoa, just... Okay, so yeah, no. Oh. So... Yeah, I don't know. We need... We need something that's going to make these transitions smooth. So it needs to slowly... So over here, it needs to slowly ramp into... So we're going to go 0... So we're going to go 0 to 100%. So we need to blend from 0 to whatever t is. To whatever t is... to 1. So I feel like we need a like an S curve. We need to go like whoop, and then we need to go flat line here, and then we need to go there. And I'm not really sure how you would do that. My thought is maybe we could take this and we could merge it with another curve that is inverted. So LMNO equals what if we do like 1 minus n, and then if we move that down, oh, you know what? Minus 1 like that we need on that side. Okay, so now that we have this, we don't want a minus 1. We want a minus... God, it's already way down there. Minus 0.5. Okay, so now that we have these, what we could do is we want to kind of like blend to where it's like we have this curve, and then right in this middle point, it blends to over here. And so how would we do that? So if we take m and n and if we linearly interpolate m and n, if we literally interpolate if we interpolate n to O using the graph of m, we should be able to get that kind of like S-curve thing we want. Well, the other thing is that I'm not sure. Not sure if that'll fix it. You know what? Let's just. Well, I gotta give it a shot. LMNO and P. So P is going to be P equals. First, we're gonna take. We want O times 1 minus T plus the n. Hold on. Oh, you know what? No, it's n, because n is the purple one. So n, because we want to start there, n times 1 minus t plus, and then we're going to take the O, which is the red, O times 0 plus t, like that. Okay, so if we do that, and now we move this slider, we see that one kind of like goes into the other, right? And now, instead of using t, if we use the value of this green thing here, which is m, right? So instead of using the value of t, we're going to use m. And see if we have a nice little... There we go, we got like this nice little curve here right now. So now we can use this curve, hopefully, as a way to... we can use this curve to interpolate m. So we already used m to create p, but now we can use p to smooth out this t value, right? Because this is going to be... oh, you know what? We're close, but why am I at 0.5 here? Because my graphs are... Because I'm not paying attention. So 0 and 0.5, I actually want this red to be at 1. And it looks like a minus 0.5. I actually might not want to minus anything at all. Yeah, because this is... because we want this to be at 1. We want this to be at... Okay, so we want... That's what we want there. And then the interpolation. Okay, so the interpolation is... We start out... We kind of like ramp into it, and then we kind of ramp. So there's kind of like this little tangency. I'm not sure if that's gonna work, but you know what? We gotta give it a shot and just see if we can get this curve m that we want to multiply our interpolation here, this right here, we want to find a graph we can multiply that by and have it make sense. So I think we're getting closer. These and these, creating this. And I'm actually wondering if, maybe this curve right here that we have is good enough. Maybe if we just take p and we multiply, if we take this that's multiplied by t and we do the same thing but we multiply by p, we might actually get something. So let's take we might be pretty much close to done. So LMNOP equals, and we're just gonna keep the 1 minus t. We're gonna just duplicate the formula first, and then we're going to edit it. So that way I can take this right, and let's Okay, so what I'm saying is that maybe all we need to do is multiply by p, and then we'll get what we need. So let's just try that out. So we'll replace t with the p value, and well, we got something. Not quite what we want. We can kind of see that in this transitional area, we kind of like have it kind of like way off. And then in the transitional area here, we also have it kind of like wanting to, it kind of wants to kind of blend, but it's like, nope, don't want to. And I remember that there's like in a tutorial I was watching, they just like added an offset and they had no clue why it was that offset, but they just did it and it worked. And it was like magic. And let's just try that right now. So let's try I think you might want to minus 0.5 here, like that. Nope, that's not it. Well, actually, 0.5. Yeah, that, yeah, that is weird. How about plus 0.5? And that is interesting, but not what we want. What about over here? I don't think that would make any sense at all. Okay, so we're trying, but we are failing. So as we take the graph, so what happens if we use this green graph right here? What happens if we use that green graph instead? So instead of using p, if we use m, what do we get? Do we get something better or worse? You get like this curve that needs to be kind of like subtracted out of there. It's kind of what we get. So it's too high, so well, we're using M right now. Yeah, I don't know. Okay, let's make an R. Let's just do the same thing. And R is going to be using, so we used M, and then P was like our nice little curve, right? They were trying to like craft. So let's take P, or not, or you could just crash on me. Okay, P. Okay, so both of these curves are not looking good. I'm going to say that the green one actually looks a little bit better. And so what we really need to do is we need to get rid of the difference here. So now if we get rid of the difference by too much, then right, because we got a smooth, yeah, because through this intersection it's nice and smooth. And so what we really need to do is if we could get it so that over at this point right here, we multiply that by 1. No, we multiply that by... here we need to subtract... Here we need to, like... So we need to subtract out this area, but if we subtract out this area and clamp it right to here, we get sharpness again. So we need to ramp into our subtraction, where here we're subtracting 0. We're merging the gap by 0 here, and then as we go further and further here, we strengthen how much we merge that gap. No, because then we get, because then that's no longer smooth again, is it? Well, all of this is too high. Even this side. It's all too high. If we could... we could take Q and divide it by some type of value that that kind of like puts it back down where it needs to be. So let's just take like Q. We're gonna make this equal to Q, and then we're just gonna divide by 2 and just, I don't know, just see what happens, man. Q divided by 2. No. So we have this, and we know that we need... Well, where is our little rampy dude? So here's little rampy dude, N. And remember how I wanted to minus that gap? Well, here we're going to minus the gap by nothing, and we're going to slowly ramp up how we... how extreme that is. That only goes to... Okay. So... well, okay, let's do the first thing. What do we have to subtract from Q to get it back to the original graph? Like, what is this delta here, right? And this delta would be if we took... if we take this the dotted min graph and we minus Q, then we get back onto the graph, kind of, don't we? And that min graph is this min AB. So Q R S T U. We're running out of variables, but let's say we'll call this U. And U is this guy right here. Okay, so U, and if we have a, if we take this and we want to minus the difference. So we want to take Q and we want to minus this delta. To get it out of there. So we're going to take Q minus u is the biggest part, so u minus q like that. And that wasn't quite right. Maybe it was q minus u. Okay, yeah. So, and does that make sense? Q minus u minus q. Okay, sure. So where is q? So that's q. And when we minus u, now let's just multiply u by t for a second and see what kind of happens there. Okay, so that's not what I want. I want something where it's gonna blend into. I want to kind of try to blend into that hump now. Is kind of what I'm trying to do, right? I'm trying to. Or am I? I don't even know anymore. So let's say. Okay, so we have q minus u, right? Yeah, that's what I thought. And then oh, this whole delta. Oh, you know what? It's because we want to multiply by this whole delta. So this is the delta that's getting rid of stuff. So if we that's not where I want that. Okay, so let's take that for a spin. So let's look at our slider now. Okay, there. So now we're kind of blending into there, and we want, because now we want to kind of like make it so that when we blend, god damn it, this keeps on stalling on me. When we blend into this, we definitely want this like transition, right? Like woo, we want a transition, right? And so let's say that we want to slowly ramp into transitioning 100%, and then we also want to like ramp back out of that. So okay, so I'm happy with this. I think is a key. Let's try V. Are we out of numbers yet? Nope, not out of numbers yet. So we have a. Where's our graph? Do we have a graph that kind of like goes up and then down? Because we want to ramp up, but then we also want to ramp back down. Okay, well, n ramps up and then ramps back down. Though we don't want to like. The problem with this is that it doesn't ramp all the way to. It doesn't go to 1. It's like, it's nice, but it's not exactly what we're looking for. We want. Um... Yeah, I don't know. If we could get like a parabolic curve, how could we take, okay, so you know what? I like this blue here. But I would really like it to kind of like hit, I would really like it to go all the way up to 1. Because I want it to like ramp up to... I want it to ramp up and then go back down. So M is... Well, if we multiplied M by 2 before we did that... So let's, W equals N. And I feel like, right, and M is that. So I'm thinking that M times 1 minus M, but if we multiplied M by 2 or maybe 4, well, actually, where is M? Where is M in that middle point right there? So M right here is now at 0.5. So I feel like if we multiplied M by 2, then we would have the top of the curve ending up at 1. So M times 1 minus M like this. Like if we did that, but then if we take each of these M's and we go M times 2 like that, and then over here we do M times 2 as well. And nope, not what I expected at all. So M. And M times 2. What does M times 2 give us? Okay, yeah. And we want some way to... When it goes past 1, we want it to kind of like go back down. And I'm not sure how we're gonna do that. Get some food here. So V is really close. Because our equation V, we can use it to blend in between here. So We want t to be 0 here. We want t to be 0 here. We want t to be 0 here. But then we want ramp. Well, actually, do we? Yeah, that's sharp. We don't want that at all. Okay, so when we're here, this t0 looks good here. T1 is looking nice here. So we want to go 1 to 0 to 1. Oh, 1, 0 to 1. Okay, okay. So if we want t to go from 1 to 0 to 1, then I think we might actually be closer than I thought. Because this right here doesn't go 1, 0 to 1, but if we flipped it around, we could get it to go, how about 1 close to 0 and 1? Is that acceptable? So let's look at this again. So what if we had right here we have 1 for here because the blending here is okay. And if we did close to 0, I feel like if we do close to 0, it's going to be slightly good, but not quite, right? But it's a step in the right direction. So we want one, 0, 1 for t. So we need to create a graph that's going to do that. So if we could, I don't know. Okay, I'm gonna be back in like 5. I feel like I'm getting close, but I don't know. And okay, so I'll be back. Okay, so I'm technically not back yet, so I'm just going to look at this. So I have the suspicion that that our red line, well, you can't see it, but I have the suspicion that maybe if we multiply one of our graphs um, by 4, that we're going to get something we can use. Now that's just from looking at the graph. I don't know if that's true or not. If I think about it, the two lines cross. Yeah, I think there might be something out of that. Okay. So let's okay, I got 8 more seconds and then we'll get to it. Okay. So okay. So one thought is that this n, which is derived from m, is that this formula m minus 1 minus m is getting a maximum height that is whatever the max height of m is, n is max height ends up being 1/4 of that. And so let's think about that for a second. M is, what is M? M at its highest is 1. Okay, so if we look at, if we know that M at its highest is 1, if we do 1 times 1 minus M, right, we get 0, right? M times m minus 1. If m at its height is... Okay, so what about the other case? So if m is 0, 1 minus 0, and that's m times... Okay, so that's... well, what is m? So 0.5, it hits 0.5 right in that middle point. And if we use 0.5 for m here, 1 minus 0.5, right, is 0.5. And 0.5 times 0.5 is a half times a half is a quarter. Let me see, 0.25 times 0.25. Not quite a quarter. So let's just make sure that's right. So 0.25 times 1 minus wait, but it's not a quarter. Why am I doing a quarter times a quarter? We're saying that at that midpoint, right, m was 0.5. So if we do that, okay, right? If we do that, what do we get? We get a quarter. Okay, we get a quarter. Yeah, that's what okay, yeah. We get a quarter. So my suspicion that just looking at this, yeah, we got to multiply it by 4 to get it all the way up to 1. That's definitely correct. If we multiply this by 4, we're going to get it up to 1. Okay. So now what I'm thinking is this black line right here, the solid black that we've been interpolating between the dashed and the green. I'm thinking that if we use this red line as a value of t for this black equation, then we will get a smooth interpolation. If we don't, then I don't fucking know. I give up. Okay, so let's w, x, y. Can we have a z? Can we do a z? Okay, we can have a z. So z is going to be q minus u times t, like that. So z is just duplicating this function that's working with t, because now we're gonna try to plug in, instead of t, we're gonna try to plug in this w and hope to God that it works, because I'm sick of this w. Oh God, no! It's ugly. It's horrible. It's like it's not smooth is the problem. It's like you know, it almost looks like the curve needs to be flipped around, is what it looks like. So what I mean, the curve needs to be flipped around, I think that this curve, this red curve, I think it needs to be flipped around, because that kind of looks like it's just, well, if it's, but didn't we say that for the interpolation here that we wanted, like, oh no, we want 1, we want 1, 0, 1. Yeah, we want, okay, so for this interpolation, at the point where right here we want 1, here we want 0, then we want 1. We want 1, 0, 1, right? And if we are looking at this, is this 1, 0, 1? This is not 1, 0, 1, right? This is 0, 1. This is 0, 1, 0, but we want 1, 0, 1, right? And even when we looked at this curve result for z, the curve result for z right here, that's going bowing up. Even when I looked at that, I'm like, that looks like we used the opposite curve, like the curve needs to be flipped, right? And that's how I intuitively looked at this blue line. I'm like, I think the red needs to be flipped. And judging from looking at the graph of t again, yeah, this red needs to be flipped. So let's concentrate on how to flip this, right? So to flip this, I think we just need to do a 1 minus, and that will flip it around for us. If so 1 minus n times 4, like that. So if we flip that around, okay. Yeah, so 1, 0, 1. Okay, now if we look at this. Okay, so it's like, okay. So we've definitely smoothed it out. I'm not sure if that's exactly how it should be smoothed out. So let's blank out everything for a second here and just look at what we have here. So that line is... It's a little bit sharp there. It's a little bit sharp, but it's like, it's, yeah, it's a little sharp, but it's... Yeah, it's a little sharp. So why is it sharp? It's because this incline is a little bit intense. So what we could do is we could try divide by 2 instead of 4 and see if... Oh, nope, because once we do that, this looks ugly as hell. So we definitely need to hit 1 here. Now when we're looking at the interpolation here, right, it's blending between this and this. No, I mean, like, if we're trying to blend between this and this, then actually I think that's right. I think that's the correct blend. So I think we just forgot what the two graphs look like. Well, that's not what we want to blend. We're trying to blend that. I mean, maybe that's good. Because if we look at the t-values... Because this is that graph. So this is one graph. This is the other graph. These are the two graphs we're trying to... Well, these aren't the two graphs we're trying to blend between. This is like... This is our graph that has this bump in it that we needed to remove. And this is a graph that looks alright. And so we try to just remove that bump. And... we kinda succeeded, but it's like I feel like maybe if we could increase that transition zone for the red, right? Like if we could increase this transition zone somehow to make it a little bit wider, then maybe we could N, so where is N? And M is this min-max formula. So I think we need to like increase that transition zone somehow. And if we could start the transitional curve a little bit over here, then I think we would get something that looks a little bit better. But I'm not sure how I would stretch that out. I mean, if I dig deep enough into it, I could probably stretch that out, but it's like, But like if we... So what I'm thinking is if we take this and if we divide it, we're going to compact it. Why is this? Dividing it, not a good idea. We really want these caps to like push out a bit. So where's that intersection happening, right? Where does that happen? So it's a minus b. It's where those two functions are. Okay, so you know what? It's been 4 hours, so maybe we should I think what we should do is, you know, I don't know exactly what I did wrong. It's kind of close. It's a little bit jagged. You know, it's not the best blend here. I think we could do a better job, but I think it's time to just clean this up, right? We got all these variables running around. Let's try to clean this up because this blend, like if we look here, it's not jagged. It's like, it's just really sharp, and it looks kind of like a pinch. Like it's not quite. Oh, except that. That's horrible. Okay, hold on. What is that outside the range of what we need? No, that looks... Well, actually, no, that's not... It's like... It's definitely not what I want. Now, if we look at it, it's definitely like... It's kind of blended, right? Like, if we look at it, we definitely got a smooth transition. But we still got that, like, jagged bump. We got a little bit of noise where we have... Instead of smoothing this out, we just kind of like have this bump before and after. So I almost say this is our interpolation value. What if we crank that up by like 2? Nope, we just get a dip. What if we are less extreme? Nope, just nothing good there. Okay, so we've smoothed it out. And we use 0, 1, 0. Um, yeah, I don't know. You know, let's just finish it. let's not worry about it. So we want, let's start expanding this equation here. So I'm gonna take my notepad here and let's see if we can okay, so I'm gonna close this. I'm gonna make it so you can't see the screen, but or well, you'll be able to see the screen, but you won't be able to see the no, you won't. Okay, so I'm hiding that screen, and let's take a look at this. I'm gonna plug in some of the equations. Q minus U times W. Right, so I'm just gonna start replacing things until I get the final equation. So Q minus U, W. Okay, so now W, I'm gonna take formula W, and W equals 1 minus n times 4. Okay. 1 minus n times 4, not 1 times 4. Okay, so Z equals Q minus U times W, and W equals 1 minus n times 4. Okay, so with this W now, we're gonna do our final substitution right up here, and we'll keep the references over here. So wherever we see W, we can use substitution and place in the new equation. So we'll take that, we'll just throw that in there. And now we have Q, U, and N. So let's, so Q equals A times 1 minus M plus B times 0 plus M. Okay, so let me look at that, double check that. So Q equals A times 1 minus M plus B times 0 plus M. And that is Q. Okay, so we're just going to take where we see the Q's, and we're going to plug this in. And this is just ridiculous right now. But okay, so we got the Q's. Okay, so now we have M and we have N, and then we have A and B they're just themselves. So for M, what do we have? M equals the max 0 min to A minus B plus 1.0, and 1, 2, 3, 4 divided by 2. Oh no, what the Jesus. Okay, well, let's hope we wrote that down right. Can I do Control Z? Will Control Z work? No. Yes. Yes, okay. So, I'm just wondering why the display isn't, what the hell? Yeah, the display isn't putting the right number of parentheses, so it's just kind of annoying me. 1, 2, 3, 4, 5. 1, 2, 1, 2, 3, 4. Yeah, the parenthesis you can kind of whatever. Okay, so I'm just gonna make sure this is right. 0 min 2 AB 1.0. Okay, yeah, sure. So M. Okay, so we got the value for M. And now wherever we see M, we can do the same thing, M. And then we see M over here. And then we see M over here. We see M over here, and this is not a good day for us. And what else do we have? What other variables do we have? We have A and B, which are, you know, our inputs. That's why I don't like one-letter variables, because when I try to highlight things, it does that. Okay, and so there's a U here. And, U equals min AB. I don't even know why I'm using... Okay, U equals min AB. Alright. So let's find where that U is. Sure, right there. Okay, yeah, And there's an N still. It's because we have not... Why the hell is there an equal sign? Start over. Okay, so where is our N? So we obviously have an N here. N is equal to... N equals M times 1 minus M. You know what? Screw this. So this is obviously really convoluted. Let's just make sure that we just have everything in the correct order. So U is min AB. Then we have M. And then we have NO. N, but O isn't used anywhere. O is not used. O is me just trying to figure stuff out. Well, hold on. O and, what is, W here? Uh-huh. What if I took O? Just curious. N times 4? That's probably the same graph as, yeah, that just makes them the same graph. So, O, whatever. O doesn't matter. N. NW. N. There's no P here. What is P? P is some weirdness. There is a Q. And Z, Q, and a U. Q, U, and W. Yeah, let's just throw this all in a formula, and just see what we can get if we take all this, and if we are just trying to throw this in, like, maybe we can get something. So let's just take all that. And let's, we'll just call it, float SDF, SmoothMin attempt. We're just gonna call it SmoothMin attempt, because that's what it is. It's an attempt. Float A and float B. Because we do not actually have something that works. It kind of works, but it's definitely not exactly what we want. So what we'll do is we'll just say float. We're not going to try to simplify it because, you know, you notice that once we try to simplify it and it's very error prone to cut and paste like that, and also it just got out of hand. So this would be more efficient anyways than trying to like cut and paste and then have everything calculated multiple times. It would be more functional that way. What we really would want to do is kind of simplify the equation. Like if we were really satisfied with this equation, we would want to simplify it. Anyways, so we're just going to return z. And this is our attempt at SmoothMin. And I didn't quite get it, but I think, I may have gotten it enough to where we can at least get something, So let's see where we screwed up. No matching overload function found. What, for min? You're fucking kidding me. Oh, I see. They're not talking about that line. They are talking about all these places where I used integers. The shading language is not going to like that. So let's put the point zeros where we need them. Okay, so save that. Okay, so now let's take that. We're going to paste that into the shader, and we're just going to make sure we can get that to compile. And what did we screw up now? So it's very odd that, we cut and paste. Oh, so it doesn't like that. Okay, so now that's compiling. So now we're just going to try to clean this up a bit. Not too much, but I just want to line up all my semicolons like that. Take that. We're going to paste it in here. Okay, so that's working. So we're going to take SmoothMin attempt, and we're going to look for right here where we use min, and we're going to replace that with our SmoothMin attempt. And we're going to save that, and then we're just going to see what happens, all right? And then I'm sick of this. All right. You know what? It's not too bad. It's not too... It almost does like a stickiness where it's like, yeah, I'm not too, I'm not too unhappy with that. Now, what I do want to do really quick, because I don't get much time to look at that effect, I want to slow down the animation so that I can kind of see, I want to see what's going on there when I'm doing that. So let's, so in the SDF distance to nearest object, we're animating using iTime. And we're just going to say float t equals iTime divided by 60. Let's try slow motion. So basically, we're going to just try to slow down the animation. We're going to do SM for slow motion. Well, actually, no. Let's just do T, because we might want we might want to mess with T in different ways. So T is just for time, but modified iTime. So let's just take that, and let's not forget our point 0. I almost forgot that. Hopefully it'll get hammered into me eventually. So Control A, Control Copy. We're going to go Control A. We're going to delete that and start over again. Okay, so now it's going really slow. And let's just take some time to, like, look at... I'm actually surprised... Okay, so is that really the speed of the light? I guess. So maybe that was too slow. I don't know. Nah, let's keep on looking at it, because this will give us time to actually really take some time to observe kind of how it's... Alright. So we got a little divot. Uh-huh. Uh-huh. So there's our curve. Okay. Uh-huh. And then it kind of like, uh-huh. Alright. Alright. And then right there when it... Yeah, that's not bad. That's not bad. It's like, you know, for my first... Well, it's not my first attempt, but for actually just trying to make a formula with messing around with the graphs and whatnot, I would say that's not too bad. I would say that let's speed this up a little bit, because I think 60 times slower is a little bit too slow. Let's try like 10 times slower, right? So if we do 10 times slower, we want slow enough to where we can really like get a good look at it, but not where it's like paused, you know what I mean? So there we go. Right, so they're basically circles when they're far away, and when they start to get closer, they merge together. Okay, awesome. So that's pretty cool. Like I'm happy with that. What would also be interesting is I wonder how I could like get the colors to merge. So the distance to the nearest object, you could probably do like a mix where, depending on, right now, the distance, I think you would use like a mix for that. Yeah, I think that would be a little bit out of what I'm able to do right now. But what I would like to do is, instead of having one of these objects as a sphere, it'd be nice if we could make it a box. So let's see what we're doing here. So this is done. The SmoothMin merge, we have just completed that. We're good. So the next thing we want to try is make one sphere a box. Right? And let's change that line. Let's, I'm just editing the, my little layout for how I know when I'm outside of the column, so I know where you can see things. So you know it's more here, isn't it? Okay, so yeah, we're gonna try to make that into a one of those spheres into a box by using a sign distance function for a box. And the box needs so we're gonna do a float SDF box, and then vec3 pause, and then vec3 dim. So the dimensions of the box, and then where it is. So it's not going to have any rotation, right? So what we can do is we can say that the box is kind of like on the center of the box is at the position. And so how do we know if Z is inside the box or not? And so for Z to be inside the box, if the Z distance from the SDF box so we also need the point on the surface. The point on path. This point on path, we need it in relation to the point on path. So if we have the point on path dot z minus the position dot z, and we take that delta, and if that is if the absolute hold on. Let me draw. I gotta draw this out. If I can get a pen that actually works. So if the distance is less than the half of the Z radius of the box, then we're like inside of the box. So, and when we're inside the box, we want the value to be negative for the signed distance. So, we're gonna take the length of the point on path dot z minus position dot z. So that's the distance from the origin of the box. So we're going to take the length of that, and then we're going to take the dim.z divided by 2. Okay, so dim.z divided by 2 gives us the z radius of the box, for lack of a better word. And if our point on path's distance from the center is less than this radius, then we're like inside the box. So we take this radius, and we actually want this radius on the other side, right? Because if this is less than this, then we're inside the box, and when we're inside the box, we want a negative number. So this minus this gives us a negative when we are inside, and then if this is greater than the z radius, then we're going to end up with a positive number, right? Because a bigger minus a smaller is always going to be a positive. So that will tell us um, if we are inside the box or not, right? So float, we'll call it zdist. And then we just need to do the same thing for all the other axes. And this is probably really verbose and not how we should write it. But this is, the first time I'm doing this. Like I've seen people do it before, but I've never done it myself. So I mean, so let's just let's be verbose. Okay. So the next thing is we have to take the min or max of all three of these, and I have to think about what that entails. So we would need to be when we're talking about if we're inside the we have to take the max of all of them, right? Because if any of these maxes are positive, a negative here indicates we're inside the x bound, a negative here indicates that we're inside the y bound, and a negative on the z also indicates that we're inside the z bound. And we need to be inside of all three of these bounds in order for us to be inside. For us to be inside, we have a negative. So if we take the max, then as long as everything is negative, the max will end up with a negative, but if anything is positive, we end up with a positive. Because it just takes one of these to break being within inside the box. So we're going to return the max of xdist. I don't know if it takes... I don't think we can use max with... I don't think max is like a var arg kind of thing, because this isn't... let's just see if that works. I don't think that'll work, but let's just try that. What I mean won't work is that I don't think we can call max. I don't think max is overloaded to take 3 arguments, but we can find out, right? So let's run this and see what happens and see what our errors are. Max, no matching overloaded function found. Okay, so that's kind of what I expected. Also, once again, does not like those 2 semicolons. That's just a habit for how I usually denote the ends of curly braces that end on a different line than they begin. But I forget that functions don't... very strict C code won't let you put semicolons at the end of function declarations or function bodies. Okay, so now that we know that this just isn't gonna fly, we can just we just gotta break it apart again a little bit more. And so we have the max of this, then we have the max of this, and then and our brackets, they look balanced. Okay, so Control A, no, save, Control A, Control copy. And let's just paste that in our shader and see what we got. Okay, so now it's compiling. So let's take SDF box and let's try to, why don't we just throw another bot? Why don't we just throw? Let's just create a object. Let's just create another object, or let's just create a distance 3 over here. So float distance 3 equals SDF box, and then we'll use the point on path. The position of the box can be like vec3 0 at 0, 0, 0. And the dimensions of the box could be like a vec3, and it could be like a unit box. And let's just give that a shot. We have the SmoothMin attempt. So right now, because I'm lazy, let's just put the box in there and just get rid of one of the spheres. Just because I just want to see if I can even get the box to render correctly before I try to finesse it. Let's just make sure we can get a box to render correctly, and I think we might have a box rendering correctly. Yeah, I think that is a box. Now, I think that that we're looking straight down on it, so we really need to move it a little bit. So let's move that box over to the left a little bit so that we can get a better view of like the actual. Oh, that's kind of cool. So I want to get a little bit better view of the perspective of this thing, to make sure that it's working how I think it is. So let's take this box and let's take the position and just go 0, -1, and then 0, 0. And that will get us something that's kind of over to the left on the screen, and maybe we can see a little bit more of the perspective in that box. So I actually need to move it over more than, let's try 3. Can we move it over 3? How about 4? No, let's just try 3 first and see what we got. Okay, so we're still kind of... Oh, I see the other angle. If we move it up a little bit... Can we move it up a little bit? Let's say that's X. Let's move it up by 2. Okay, so I'm going to take that, and I'm going to run it. And that box is way too high. So let's just add 1. Save it. Run it. And okay, so now we can kind of see both we can see like 3 sides of the box, not as well as I would like, but it's I definitely got the SDF calculation for the box correct. And that's kind of really what I wanted to know. Like, do I have that calculation correct or not? So when it's merging, there's kind of an artifact there when it's getting close. So I feel like that might have to do with that crease that was in my graph. See how there's this crease here? I think that has to do with when I was in Desmos trying to like make the SmoothMin. I think it's not quite the SmoothMin that I need it to be. Let's try let's just try to run another SmoothMin attempt on... Let's do SmoothMin on this, and then... Right, so let's add all the objects back. Okay, so if we add all these objects back, and then I'd say I'm done for now. I mean, I feel like I need to learn a little bit more about how this is done. Alright, so we kind of see it merging there with the... Yeah, so I still don't quite know what I'm doing, but it's better. It's better than, you know, that's pretty good. Hopefully I'll get better. It's almost 5 hours. But yeah, so, what do we got? So, make one sphere a box. Well, we didn't quite do that, but we made a box, so we're done. We made a box. We added a box. That's what we did. Okay, so that is our agenda there. And so, lastly, I know that maybe the code window hasn't been the best for keeping track of what's going on, because I just didn't do a very good job at pasting everything. So I'm going to take, I'm going to go to pastespin.com right now, and I am going to actually I could let's full screen this. So over here in pastebin.com, I'm going to edit this. And I'm going to go Control A, Control V. And we're just going to paste all of this code right here for what we just did. And this source code also references where it's hosted on Pastebin. So if you go to tinyurl.com/sdf-004, you'll get to this code. Here's the actual Pastebin URL here, but that's kind of hard to remember, right? This weird crap here. So that's why I did a tiny URL of it as well. And we're just going to update this. So we're going to save the changes. And then the last thing we're going to do is before we're done, we're going to make sure that... Cancel. Actually, let's save this as SDF... We'll save this graph as well. I'm going to save that graph. I'm going to put that into the paste as well. So, we're going to add that to the source, or the little references that we have, right? So we have the main source that I want you to see is where you can actually find the code. And then there's just the other stuff, right? So save that, copy all that again. We're going to edit. Actually, you didn't see that, but we're going to edit this. And I just updated it to also include the URL for the graph so that you can see that. So the Desmos graph right here, I saved that. I don't know if you can actually view that if you're not me. So we'll give that a shot as well. So let's save these changes. And let's take this graph here and let's just do like a new incognito window and let's see if like it's like hidden or anything. Alright, so nope, you can see my stuff. You can see my graphs. I guess they're public by default. That's cool, because I actually want you to see all the work that we did to try to like get this to work. So if you want to take a look at that graph and see those different functions, you can see those as well. But yeah, we're good there. Let's close that. Save, leave, and Pastebin. And let's do one more thing. Let's make sure that the tiny URL gets us back to this Pastebin. So I'm going to open up a new tab, and I'm going to paste the tiny URL from the documentation, tinyurl.com/sdf-004, and that gets me back to this source code as well. So we have all of the things we need for if you want to take a look at this and get it, working. You have all the information at your fingertips. And for next time, what do I want to do next time? So we're pretty much done. For next time, I just would like to get a better SmoothMin function. I would also like to like move the camera around a bit, and I would like to. I guess I should really focus on one or the other. I think that since I got a SmoothMin that was close but not quite right, I should try to do a SmoothMin function again and get it working. Because we didn't quite get that SmoothMin function working. It's very close. Like it looks great with the sphere, but the sphere is already smooth in the first place. So that little sharpness in the curve doesn't matter, but for the square, right, it seems kind of artifacty to me. Yeah, so we're done here. I'm gonna close the stream, and yeah, I mean, hopefully this was useful to anyone. I can't see. Oh, hey, there is stream chat in here. Um, yeah, but I'm gonna try to do this again at 10 p.m. Eastern Standard Time, Michigan time. I don't know where anyone is from. I see there's one person in the chat room. Is that me or is that somebody else? I don't know. Um, but yeah, I'll do this uh, tomorrow at 10 p.m. and just try to get this. I'll also try to put this up on YouTube. I don't know if YouTube is gonna let me put a 5-hour video upload, but I'm gonna try to do that. And yeah, maybe I'll be more organized the next one and have a little bit better quality. But I'm out of here. So I think I got a lot done. Well, actually, no, I didn't get. Did I get a lot done? I don't know. I don't know if I got a lot done. I don't feel like I got a lot done. I feel like I did a lot of review of things that I've already looked at, and that I took a lot of time explaining things, and maybe I went a little bit too slow. But I'm hoping that if I keep on redoing this and always build the shader up from the ground up, so I never want to start from. I never want to start from the. I never want to start from the. I don't want to start with something that I built in a previous tutorial. I want to see if I can keep on doing this from scratch and just have it so that I get faster and faster building up all of the boilerplate and getting back to where I was previously, right? So the goal right now would be, since this is about a 5-hour long stream, the goal for tomorrow would be to code all of this all over again and get back to where we are right now before this 5-hour mark, and then add on some new stuff. So I'm going to watch some more tutorials on this kind of stuff and see if I can figure it out, and then we'll just try it again. It looks like the SmoothMin thing is what I'm really screwing up. So, all right, later.